Now students, we will go for the two number of loops. For example, for n is equals to 2, to generate the two loops, we will plug the string from the different position as we have plugged the string in the first diagram or the for one number of loop. Now these are the two fixed points. It is the midpoint. Now we will plug the string from left half of the string. From left half of the string means from here we will plug the string. Now at the time t is equals to 0, the position of the string will be like this. That means one wave is formed here, and after the continuation of the vibration generated in the string, we can observe the two number of loops in this string here, and the points where the amplitude is 0, those are called nodes, as you know, and where the amplitude is maximum, these points are called antinodes, as we have discussed already. Now this complete length of the loop is converted now the one wavelength, because if you observe the black position of the string, there is one wave is formed, and we can say that the length of the string is converted into the one wavelength. So we can write here the L is equals to lambda, or the wavelength, and to calculate the frequency we will use here the wave equation, that is V is equals to F lambda, and now the frequency is equals to V over lambda. So because we have generated the two loops, so we will write here the F2, and we will substitute the value of the lambda from the first point, that is L. So it will be the formula to calculate the frequency when we have generated the two number of loops in this string. And now we want to show this frequency for the two number of loops in terms of this fundamental frequency, which we have calculated in the first part for the n is equals to 1. So we have here 2 with the multiple of length. Now we want here the 2, so we will multiply by 2 in the numerator as well as in the denominator. So we will get the equation for F2 like F2 is equals to 2 times of V divided by 2 times of L. So we can simplify this equation like 2 times of V divided by 2L. Now we can show the frequency of the waves generated for the n is equals to 2 in terms of the fundamental frequency, like F2 is equals to 2 times of the fundamental frequency. Okay, because V over 2L must be equals to the F1 from n is equals to 1 equation. Okay, now it is called the first overtone. The first overtone, and with the name of harmonic, it is called the second harmonic. It means if we find for the further number of loops the third harmonic, fourth harmonic, or the second overtone or the third overtone, it can be shown in the form of the fundamental frequency. So now we will calculate the frequency of the wave generated for n is equals to 3, that is 3 number of loops, and it is called the second overtone. It is a string here. by plugging the string, we can generate the 3 number of loops in the string. Now we can observe the complete length of the loop is converted into the 1/2 of the wavelength. That means if we start from here, from the left side fixed point, that is the point P, it is a one wave up to the second node, it is the first node, second node, third node, up to the third node, it is a one wave, and up to the fourth node, that is 1.5 wavelengths or 1.5 waves. So we can write here the 1/2 wavelength. That can be denoted as 3/2 lambda. I am repeating here. Okay, if we start from the first node formed at the fixed point, and it will be the second nodal position, and it is the third nodal position. Up to the third nodal position, the one wave is completed, and for this last third loop, it is a half wavelength. So 1 wavelength plus half wavelength is equals to 1.5 wavelength, or 3 lambda over 2. Now we can write here the complete length of the string is equals to the 3 over 2 lambda, and now we can calculate the value of the lambda here, that is 2 times of length of the string divided by 3. And to calculate the frequency, we will use here the wave equation, that is V is equals to F lambda. And we can write here the frequency is equals to speed divided by lambda. And now we can substitute the value of lambda in terms of length of the string, that is 2L divided by 3. After simplification, we can write here the 3V divided by 2L, because this 3 will multiply with the V when we shift this 3 into the numerator. And now we can further simplify this expression like 3 times of V divided by 2L. Why we are writing this equation in this form? Because we want to show the frequency of the stationary waves generated when there are 3 loops in terms of the fundamental frequency, because the value of the fundamental frequency is F1 is equals to V over 2L. So we can write here the F3, this 3 shows the 3 number of loops. So we can write here F3 is equals to 3 times of F1. It is called the second overtone and the third harmonic. As we have right here, as we write here the second overtone, and it is called the third harmonic.